It is 6:10. I figure we should probably start. Hello and welcome everyone. My name is Nadir Akhtar. You might remember me from the first week of class. Today I will be giving a lecture about scalability for Bitcoin, cryptocurrencies, and blockchain. All right, it's a mix between a technical and a non-technical lecture because on one hand you have to be able to understand the motivations behind scalability and what exactly scalability means, and also you need to be able to understand how it manifests. So don't be afraid if this lecture starts to trip you up. We have discussion sections like always interspersed within the lecture, and of course feel free to ask during the lecture if at any point you get confused. Cool. So a quick overview of what we're about to go through. So first we have the background of scalability. What exactly is scalability? How do we define it? How do we understand good scalability from bad? And what are some of the concepts of scalability? From there, we'll go into various ways in which we can scale the blockchain. The first one being vertical scaling on-chain, the second one being vertical scaling off-chain, the next one being horizontal scaling, and then finally, we'll go into some advanced scaling and generalizations. All right, don't worry if you don't know what that means yet, because that's what you're about to learn. Cool. So first, what is the goal of scalability? There are two things that scalability might try to do. The first one is that it wants to increase the transaction volume. You might hear Bitcoin being referenced as not having a high enough TPS compared to centralized solutions like Visa, PayPal, or whatever. Right? So if you're able to increase your transactions per volume, that means you've been able to scale your blockchain. In other words, you've been able to make your blockchain more usable for a greater amount of people. Another thing that you might want to do is see the speed at which you can update the ledger. Right? So this is decreasing the block time. So if you can decrease the block time without losing security or decentralization, you're still able to ensure that people can use your protocol without being inhibited by these costs. All right. So scalability, another part of it is the size of the blockchain. This is sort of more in concern with okay, how much information are we saving with every block update? For example, Bitcoin, as of late August 2018, was 180 gigabytes, right? It's not something you can just run on your phone. So this is another concern when it comes to scalability. How many resources are we using up when trying to do whatever it is that we're doing? All right, so you might have heard of the scalability trilemma before. This is the idea that of these three, we can only pick 2 out of 3, or more specifically, you can only choose a point within these. All right, so the closer you get to any one, the farther you get from 2 others. And we'll see how trying to increase the scalability may end up deterring us from having decentralization or security. How many people have actually heard of this trilemma before? All right, that's a good handful. All right. So let's first take a closer look at what exactly that's very black. I'm sorry, but the purpose of this is to show what the transaction size of an average transaction was in the Bitcoin blockchain about from 2015 to 2016. It's about the same now. And the transaction per second was about, let's say ends up being around 3 transactions per second when you do the math. All right, so currently, these are the variables we can play with. We can play with either the block size, we can either play with the transactions in a block, or we can play with the block time. These are the 3 things that we can naively manipulate. All right, and the goal is to try and achieve speeds that are similar to PayPal and Visa. But you'll see that there are a lot of issues when we try to naively change these things, right? Our goal is to either increase the volume of transactions within a single block or decrease the amount of time it takes to produce any given block. So this is where we can now break down scaling solutions into various categories. The first category is vertical scaling, in which you're adding more power to an individual machine. This means that each machine is able to do more work than it was doing before. Horizontal scaling, on the other hand, is making it such that you have more machines doing a certain amount of work. And diagonal scaling is a combination of the two, as you can imagine, where you're adding more machines that are also more powerful. And we'll go into this deeper throughout the lecture. All right, so you could say that blockchain are like ogres. They have layers. All right, so there's a lot of different places where we can scale the blockchain. This could be either at the first layer, layer 1, which is known as the blockchain protocol itself, or layer 2, which is on top of the blockchain. Right, so here, the blockchain is considered the base layer, and any changes you make to the protocol are on layer 1, and any connected technologies would be considered layer 2. All right, so are there any questions so far? And that was a pretty quick overview of like what scalability is, different categories of scalability.
Have there been successful layer 2 solutions you feel that are working?
Yeah, there's the Lightning Network solution. There's Plasma. There's and there's quite a few solutions which we'll actually talk about as well. There's also Cosmos. You're free to talk about that in your groups, but we'll get more into it as the lecture goes on. Yeah. All right. In which case, discussion leaders, this is now your opportunity to do the first discussion. All right. Cool. Yeah. That's.
Okay, cool. Does anyone have any questions about anything so far? Awesome. Do we all understand the difference between layer 1 and layer 2 scalability? Can someone give me an example of layer 2 scalability? Can you give me an example of something?
Everyone has one.
Yeah, like a side chain or something with the options, whereas layer 1 changing the hash function.
It's hard to do like layer 1 because like Bitcoin is yeah, like okay, why is it layer 1? Why is that? Why are you choosing
So, why do you agree? Sometimes it's like the issue is make a lot of changes, which ends up getting faster the network itself. So one example is Bitcoin Cash. That is one layer 1 they become the block that end up being
there's a security trade-off, and so you can't really get a high TPS because
it just means that you make a change that is not active. So the nodes that are running the node cannot access and basically what happens is you end up getting one chain that adopted that analytical and one chain that does not. But basically what it means is that if you adopt an blockchain, it cannot still work with the nodes that did not adopt it. That means that it has to be so that's why we have a Segway cache.
megabytes now
Some miners adopted it from cache and some did not.
because that's the biggest
Cache like solve the problem. Is it more scale? Maybe you just want to mention there's some issues involved just but I mean there's some reasons I think it does increase
Yeah, but another argument is that since you've changed the network, right, you're now operating on a different level of security as well and a different level of decentralization. Because now this network is not controlled by majority of majority of what you had before. Bitcoin Cash is controlled only by those that are proponents of this specific hard fork. Right? So then, because you have fewer miners, you also take the cost associated with that.
So it's like less far out. So
Precisely. There's Bitcoin Core, which is a centralized thing.
and they're the ones like developing.
Well, there are core developers, and they're the ones who pretty much spend a lot of their time officially developing, and they're the ones who are able to merge things into the Bitcoin code base. But they're not the only ones who can do so. Anyone could copy and paste the repo, or well, clone the repo, fork the repo, or just start making PRs to the repo, whatever they want. Like, it's pretty open. Like, though there are these gatekeepers on the official source code, anyone can make their own version of it. That's how all these different altcoins came up. I think that is it. Yeah, that's all right. Okay, it's been about 5 minutes, so unless you have any further questions, let's come back to here. All right, cool. So now we actually get to some fun stuff. So we're now going to talk about certain scaling solutions that are specifically vertical scaling and on-chain. In other words, manipulating the protocol itself in order to increase the transactions per second or decrease the block time. All right, so first we're going to go over some naive solutions, and these naive solutions are pretty much just manipulating parameters such that we expect that, for example, if the block time is decreased, we should have more transactions per second because we have more transactions in a certain period of time. All right, very straightforward. So the first question you might ask is, why can't we just increase the speed of the blocks by decreasing the difficulty? If we decrease the difficulty of the proof of work puzzle, we're not able to produce blocks at a much faster rate. 10 seconds rather than 10 minutes. I mean, who thought 10 minutes was a good idea? Anyway, so the issue is that the time to propagate a block, the network restraints, remain the same regardless of the time that it takes to create a block. And what this does is it ends up creating a lot of issues, one of which being that by the time you're trying to, by the time you've gotten a block, someone else might have finished mining the second block. And if that person's already finished with their chain, they might be able to produce another block. In essence, it'll always leave you behind in the dust. So that's one issue when it comes to this, to naively decreasing the block size. Another issue is that the size of the blockchain is going to grow exponentially compared to whatever it was before. If you go from 10 minutes to 1 minute, you will now grow at a rate 10 times faster by definition because you've got 10 times as much data coming into the blockchain at any given point. In addition, it increases the network stress because if you don't have the fastest network speeds, then it's going to take a lot more time to download all the information. And again, that'll also lead to centralization in favor of the larger miners. And another issue is that you'll have more forks. If you have a smaller block time, like a minute, that means that the likelihood of someone producing a block in that time is much higher, meaning that someone else producing it at the same time as you is also high. So you're going to get a lot of these forks in which you have uncles and grand uncles, essentially wasted work, because these blocks are not included in the longest chain. They don't actually, though the transactions were validated, their work has been lost. It's been wasted because it's not going to be recognized later. Right, so that's another issue. We don't want forks happening as often because it also prevents consensus from happening. Right. So actually, before we go into that, let's think about how we could still solve this problem. Right. So the size thing is pretty difficult unless we change the size of a block. But Ethereum, you may know, has a transaction per second rate of 17, or has a block time of 17 seconds, right, which leads to a higher transaction rate. And the way it does this is through what's known as the Ghost protocol. Right, so the issue we were having is that when there's a fork, there's wasted work on the block. By having a 10-minute block time, we ensure that the likelihood of forks or collisions is as low as possible, or at least low enough to be reasonable. If we have a larger amount of forks, is there a way that we can compensate workers that have wasted work but still are trying their best in order to get their blocks into the blockchain? And this is where the Ghost protocol comes in. What Ethereum does is that it changes the fork resolution policy. In Bitcoin, we recognize the chain with the largest amount of work as the one that is valid. In Ethereum, we look at what's called the heaviest observed subtree, which means that not only are you considering the chain off of which you're building, but you're also considering which uncles or grand uncles, I think all the way down to 7 layers, you're able to observe. So if I'm a miner and I see this fork, I can include the hash of that uncle, meaning the like not the parent, but the parent's sibling, into the block. And if I do that, I will not only give that miner compensation, but I'm also more likely to be selected as the person whose block is built off of. In essence, if I see more uncles and I include their hashes into my block, it's more likely that miners will choose my block to mine off of as well, meaning it's more likely for me to get rewards as well. So in this way, even though there are a lot of forks, you're still able to make sure that miners are compensated, that the work is not wasted, while still having a low block time. All right, so does that make sense for everyone? By compensating miners for their work, they get, they're still happy, even though you're decreasing the block time. All right, so then in Ethereum, it was about 14 seconds as of September 2018. All right, so next thing we can do is increase the block size. All right, it's an easy thing, you might think. All right, we have a block limit of 1 megabytes. If you want more transactions, why not just make more space in every block? All right, it's a very straightforward idea. One, it's an easy implementation. This is a good thing. It's not very hard to say, all right, this block, we're going to change the constant from 1 to 2. It's a very easy thing to do conceptually and in the code base. And on top of that, it lowers the transaction fees for users because users are no longer competing for as much space, right? You've increased the supply, therefore you've lowered the price given the same amount of demand. Right, but there are still some issues. The first one being that a block size increase requires a hard fork. How many people remember what a hard fork is back from lecture 4? All right, 1.5 people? 2 maybe? So a hard fork is a change to the protocol in which the changes are not backwards compatible. In other words, if I were to take my block size of 1 megabyte and change it to 2, any of the old nodes are going to reject this block of 2 megabytes because it's over the limits. In contrast, a soft fork is backwards compatible. If I change it from 1 megabyte to half a megabyte, all the old nodes will still accept it. In this case, because we're increasing the block size, it will be a hard fork. And that's messy because since it does not play well with the old nodes, now you're going to fracture the network. You're going to have miners either on one or the other. They can't use their mining power on both. It'll also lessen the transaction fees, which was in the pros, but also in the cons, because now miners are going to get less transaction fees. You might say that they'll still have the same amount of profits if they have more transactions in the block anyway. And on top of that, the size of the blockchain is still increasing at the same rate as if we were to have lowered the transaction or the block time. And on top of that, it's also a one-time fix. I mean, if you increase the block size from 1 megabyte to 2 megabytes, by the time that you've hit the limit for 2 megabytes and you're consistently leaving transactions unconfirmed, what are you going to do? Are you going to increase it again? That's very expensive. Right. And there's also longer propagation times because there's more information within each block, so it takes longer for every miner to send its information to another miner, which again, then sort of plays into the centralization issue that we see with mining, where the ones with higher bandwidth and higher storage amounts are able to fare better in these circumstances.
How much latency, if we increase the block size by 100 times, is that significantly affecting latency to 100 megabytes?
I mean, I would say it could. You might think that, sure, we download YouTube videos all the time, so it shouldn't be a big deal. But when you're mining, it could make a big difference. And on top of that, if we want Bitcoin to be as accessible as possible, then we have to keep in mind that not everyone's bandwidth can necessarily handle that. So, I mean, it depends on what your goal is. If you're assuming that everyone's from a first world country, then sure, it might be fine.
I guess miners have to have strong internet speeds to be competitive even in the other.
Yeah, that is true, especially in this day and age. I guess the question then is how closely do you want to align with Satoshi Nakamoto's 1 CPU, 1 vote? Sorry, still the same amount? You mean in this diagram?
Yeah, if you're increasing block size 2 times, then why wouldn't the amount of data be
Right, so the data will increase twice as fast in this diagram. We see that 5 gigabytes is reached in 1 year as opposed to 2 years. Yeah, no problem. This diagram happens to be the same length, even though it's, you're fine. The idea is that it's the same block time, but it's a different block size. Don't worry, you're fine. All right, any other questions? Mm-hmm.
Can you explain again what affects the block size?
What?
The same number of transactions either way.
Yeah, so what affects the block size is the number of transactions you don't explicitly say 100 or 200 transactions. You say 1 megabyte or 2 megabytes. All right, so that's an arbitrarily-ish chosen number. It was originally chosen to be 1 megabyte just to prevent spam. And the question is whether or not it should remain 1 megabyte or increase. All right, so there's nothing that determines the block size other than the goals and philosophies of the people in the community.
Is it possible to decrease the amount of size that each transaction takes within a block?
Right. So actually, that is this right there. Yeah, thinking ahead. All right. Any other questions? All right. In which case, we will take a small amount of time to have a little bit of discussion, so that you can discuss what the naive solution was, why it didn't work, and some of the pros and cons of some of the other scaling solutions that we use to build off of the naive solution. All right, cool. Go ahead.
Anyone have any questions about Well, they both have like pros and cons, and they both can use big concepts. All the stuff that we So yeah, this obviously just means that if you have two minors, my main and then both together, one of them decides from the actual scope, they start sending out these blocks to the other minor, which would suggest that at that point because minor B cannot interact with minor A. Yeah, so you can't update the entire system because it's decentralized. So there's no way to say like, every minor update your software, and also you choose your own and then you have some minors that do, and then they become Bitcoin Cash. Some that don't, and then you switch it to
So both explanations for both the using time creating the box and creating the box.
yeah, both of them would review and introduce another transaction. You can have transactions.
The problem is that it's too much data. Because miners you increase the block size by 2, by times 2,
So what
and
is
then 2
yeah,
That's the problem.
I don't think it's the biggest one. That is a problem with that. Over time, it becomes such that
is going to
it becomes more centralized. A lot of nodes the bigger issue is that
How does this go for you can let it request it posted?
do you understand what like a domino block is? So if you decrease the relaxation time, you end up having a lot of work to do. So within another mechanism, one of the big trade offs Ghost is a way to avoid mine legitimate blocks, but are so with Ghost, basically future blocks have the incentive to avoid whatever and then those are basically what blocks and then both the miner and always get rid of
Just to clarify, for so say you have it will be on first check, but yeah,
not the block itself, but there is proof that they've seen
I see. So, okay. So they just keep the cycle.
I'm not exactly sure how. Like knowledge that the actually how let's work with them on blockchain that.
Okay, it's been about 5 minutes, so go ahead and ask your last questions, and then turn your attention back up here.
but it's also like every year.
Are there any lingering questions that any of you have they haven't had answered yet? All right, cool. Yeah.
Oh, how come storage space is an issue? Just like the storage sizes also increase every year, like
All right. So one question was, why is storage size an issue when the storage like the amount that you have to pay for storage decreases every year? Is that the question? All right. Well, it's still an issue because one, we want to be able to like, assuming that we hit a point at which, I mean, that's a valid question, right? Like one thing is that the blockchain might not scale as well as like the amount of storage space that you have to buy might be more over time than the amount that the blockchain scales. Like if we were to scale it down, or are you asking like if we don't do anything to the blockchain, we don't touch it, it's growing at its normal rate, why does it matter in the long run when storage has become trivial?
Storage space like doubles every year kind of thing versus like blockchain is only 100. I mean, Bitcoin is like 120 gigabytes or something, which is not that much.
180 at least.
Something like that.
Yeah. Yeah, so it's a valid question that if our technology is improving, we don't really need storage space, or we don't really need to worry so much about storage space. I mean, this is true for like the internet too. We have a lot of things we can do nowadays that we couldn't do before, but still, if we want to, one, make sure that like in the time the blocks are being propagated, that it doesn't put smaller miners at a disadvantage, don't have as much powerful hardware, or even in the long term, people who want to mine on less expensive devices, let's say. Like if you want to mine on your phone, it's close to impossible, for example. Not to say we'll ever reach a point at which you could mine meaningfully on your phone, but at least it's a consideration. Again, as to whether it's practical is not so much the discussion here. It's just as if you were to have this goal, what would you try to do? No. So valid point, definitely. All right. So we talked about decreasing the block time. We talked about increasing the block size. The last parameter we have to play with is decreasing the size of the actual transaction. All right, you might think if we could decrease the size of the transaction, wouldn't we have done that by now? What data could there be in there that we're storing that shouldn't be in there? All right, so there's a couple of approaches that allow us to decrease the size of the transactions. The first one being SegWit or segregated witness, and the second one being recursive snarks. I'm going to go slow here because both of these are a little bit complicated, so please feel free to ask questions. I highly encourage it. So first, this is what a transaction looks like. We have the inputs, the outputs, we have the hash of the previous transaction, the identifier, so to say. We have the index where that previous transaction was, and we have the signature data. So the thing is, you might have noticed that the signature data is really only needed when you're verifying that the block is, or that the transaction is valid. You don't really need it after the fact. Like if you're looking back on the blockchain, you don't need to go back and find the signatures and revalidate those blocks. So because of this, the question is whether or not you could move that signature data outside of the block into a separate location. All right, so this is what SegWit or segregated witness aims to do. As you might have inferred from the name segregated witness, it attempts to move the data that says this is valid outside of the block. So what this will look like is actually a soft fork. And the way that they managed to do this within the constraints of the protocol, because remember, a soft fork means that you have not broken the constraints of the protocol, you've merely specified the constraints of the protocol. The way that it does this, it takes all the signature data, moves it out of the inputs and out of the outputs, and it parcels it underneath the block. So all of the nodes that are running SegWit, they're going to see this information. Now you're thinking, well, okay, old nodes, they're not going to be able to accept this format. So the thing that new nodes do when they send this data to old nodes, so that the block is still valid, but it still meets the previous format, they strip off the signature data. So old nodes, they're going to see inputs and outputs with no signature data. Right? They're not going to really care whether or not the users have the signature data in there, because to them it's just a transaction. Right? They're going to think if they were observing it, they think, yes, this is very weird, but it does not break the protocol, so to say. So because of this, we can avoid a hard fork. Right? We can avoid splitting the network while still making possible segregated witness. So does that make sense so far? All right, so two things we said, moving the signature data out of the block, and here's how we avoid a hard fork, by parceling it separately and not sending it to the old nodes. Right, but now the thing is that we don't have any evidence that the signatures were correct in the first place, that they were included in the transactions. So how is it that we can make sure that these signatures were valid? Well, the way we do this is by we're taking something that previously was used to confirm the existence of transactions and manipulating it. Does anyone know what that thing is? All right, what's the thing in a block that makes sure that none of the transaction data has been modified, or no one's claiming that a transaction was in there when it was not originally?
You go through the Merkle tree and find the root.
Precisely. The Merkle roots is that piece of data. So, oh, it says Merkle tree right there. I'm sorry.
Yeah.
But you're still so shy, even though the answer was right there. All right. So that's what we'll do. We'll create a Merkle tree of transactions and of witnesses. So instead of just having the Merkle roots of the transaction be the actual Merkle roots, we make a Merkle tree of the signatures corresponding with the transactions, and then we combine those two to be the actual Merkle root that's stored within the block header. So now, if anyone tries to attest that some signature was in there when it wasn't actually, you can now compare it against the block header and prove that it was or was not there. All right. So the pros of this, actually the original goal of Segway was not even a scalability solution. Though it does allow us to take data out of the actual block, that was not its original intent. Its original intent was to fix what's known as transaction malleability. So if you're familiar with the way that signatures are generated, it uses ECDSA, or the elliptic curve digital signature algorithm scheme, which has a curve that looks like, it's a curve that looks like something like that, not like that, but close enough. All right, so a signature is some point here on this curve. The issue is that a point down here on the other side of the curve could also be considered valid. So if this transaction signature were modified to instead have the other point, the transaction data is different, but the transaction is still valid. Hence, transaction malleability, because the transactions are malleable, and that changing the form is not something we want. So what Segway would do would be to ensure that the transaction signatures are also not modifiable by creating a separate Merkle tree for those. Right, that was the original goal. It happened to be that people realized that this helped with scalability because it took data that was extraneous out of the block. And the reason why transaction malleability is important to fix is because certain layer 2 scaling solutions like the Lightning Network and sidechains need transaction malleability to be fixed before these things can work. All right. And on top of that, a pro is that it's only a soft fork. For political and technical reasons, soft forks are preferable. I mean, nowadays you see hard forks all the time, but that's just because the culture's changed, I guess. All right. And then on top of that, there's no slippery slope, so to say. There's no increasing the block size. If you increase it to 2, you'll increase it to 4, to 8, 16. Right? It's a one-time fix. It's isolated. You're not going to have this issue where people are going to want to do it again because you simply can't. Right? You get general efficiency gains because now you've taken this extraneous data out and reduced the size of the blockchain, which is all pretty good. Right? So what are the issues? Well, on one hand, we've avoided the slippery slope, but also it's a one-time increase. You can't replicate it again. Right? At the point where the blocks start to fill up, you can't just do Segway again because there's no signatures to take out of the transactions. On top of that, because of the fact that it is a soft fork that tries to contort itself into the restrictions of the current protocol, it's very complicated and very ugly, taking up over 500 lines of code, which might sound small to you for those of you in 61B, but it's a lot more when you're talking about stuff that should be pretty simple. Or not simple, but in the sense of it should not take that many lines of code to write. And on top of that, the clients now have to change in order to make these changes so that they can recognize what data they're seeing. And one last thing, if you're trying to solve transaction malleability, there are other ways to do it. Segway's not the only one. So if you don't think it's a good enough scalability solution, you shouldn't say transaction malleability is the reason why you do it. Mm-hmm.
For the linear capacity increase, isn't it only a doubling?
Well, that's still linear, right? Linear.
But linear could be 100 times, but it's not. Isn't max a doubling?
I think it's about 3 or 4 times effective. I mean, is there a particular issue you see with linear specifically?
I just thought that could be uncapped relatively.
Right. Yeah, while that is true, just mean to say that it's not a very substantial change. Yeah, okay. Any other questions? Cool. Right. So, little fun fact of history that you might have known about is that Bitcoin actually splits into two different, I guess, coins over the Segway issue. So back, I think a year and a half ago now, there was this thing called Bitcoin Cash which came about, which did not like Segways because of the fact that it was changing the protocol, and they instead said that they wanted to increase the block size to 8 megabytes. And Bitcoin, the current one, now has Segways. I would say almost all the wallets, if not all the wallets, are using, because if they're not using it, they're probably doing something wrong. But yeah, that's just a fun fact for history. Bitcoin Cash it's primarily promoted by Roger Ver and Jihan Wu, both Roger Ver being Bitcoin Jesus / ex-convict, and Jihan Wu being the guy who runs Bitmain, the popular Antminer producer, Antminers being the ASICs. So because of the fact that SegWit would change the way in which transactions are processed, it would change the way in which they mine, and that was not as preferable as having the original protocol and a higher block size, which then is also in favor of the centralized miners. All right, cool. All right, so are there any questions on SegWit so far? All right, now, assuming you're all comfortable with that, we're going to go ahead and step over in this other direction. It's also a way to decrease the transaction size, but in a completely different way. So, before I start, who has heard of a zero-knowledge proof before? All right, who feels comfortable explaining what it is? Okay. All right, so who knows what a proof is? All right, who feels comfortable explaining what a proof is? Come on, it's just a proof. Anyone feel comfortable explaining what a proof is? It doesn't even have to be like correct. Just what do you think of when you think of a proof? Really?
I said alcohol.
Alcohol. Oh, what? All right.
It's like a set of steps to get from like the problem to the solution that shows that like it's completely valid.
All right. Okay. A set of steps to get from some inputs to some outputs to show that some truth is true. All right. Anyone have any suggestions? Any other definition? All right. Otherwise, that's the one I'm going to go with because it's pretty accurate. All right. A proof is it's a set of information that will allow you to prove that something is true. Right? Like if you want to prove that you did the dishes, you take your mom to the sink and say, "Hey, look, there's nothing in there." Right? Whether or not you hid them somewhere else is a different matter. Right? But if your mom accepts that as proof, then sure, it's valid. Right? So the thing about zero-knowledge proofs is that we are trying to say that something is true without actually revealing what it is that we're trying to prove. Like, I want to say there's $100 in my bank account. What's a way in which I can prove that? Or I want to go to a website and prove that I have some password. What's a way in which I can do that without revealing my password itself? Because some of us like to use our passwords for every single website that we go to, even when we hear about all these issues, and we trust the websites to be smart about it. So the websites, in order to take the burden off themselves, like let's say they get hacked and your password's revealed, of course you're going to be pissed. So what they do is before you submit your password to them, they will take a hash of your password. And that hash is what they will store in their databases. Now you'll think, okay, why a hash? Right? A hash cannot be inverted. So if someone breaks into a website and they see all these hashes, they can't determine what the original password was. So how is it that you prove to a website that you are alleged username? What you're going to do is you're going to submit that password again. The website will hash it. It will check it against the hash in its database, and if the hashes are equal, then you're allowed in. This means that you never have to reveal the input x to the hash function h of x, but you're still able to authenticate that you have knowledge of what x is. And it's a very rudimentary example of a zero-knowledge proof. All right, does that make sense for everyone? All right, is anyone uncomfortable? All right, please, if you are, speak up. Because I don't want to keep talking and then lose it. All right? So this is what a zero-knowledge proof is. We'll go into this more in the anonymity lecture. But for now, the reason why this is useful is because consider a transaction on the blockchain. What do we actually care about? Do we care about the numbers and the addresses, the inputs and the outputs? We don't care about that as much. What we truly care about is the fact that the transaction has happened, a proof that the transaction has happened. So this is where recursive snarks come in. So let's say that Alice wants to send some transaction to Bob, instead of actually sending a script that's going to modify the state of the blockchain, instead what she could do is generate a proof that she is making some changes to the blockchain, to the ledger. And that proof is what represents her act of making a transaction. And the nice thing about this proof is that it can be verified by anyone in the network within a matter of milliseconds. Right? So if she generates that proof, she has now lost the ability to spend that Bitcoin again, but no one knows how much Bitcoin she sent, no one knows to whom she sent it. People might not even know that it was her who sent it. Right? So this is one of the pros of zero-knowledge proofs. The reason why this is good for scalability is not because of the zero-knowledge part, but because of the recursive aspect of these proofs. Right? Because consider again, if a miner is looking at all these proofs, they're validating it, they have to do one of two things. They either show that all these were valid, or they have to submit some kind of proof that they were valid. Right? Again, since they have to submit a proof, why not make it a zero-knowledge proof, hence concatenating all this information together, and then they have this one zero-knowledge proof, which they've used to prove that this other set of zero-knowledge proofs are correct. Right? So in this way, you're able to validate, you're able to both condense the information very quickly and validate it very quickly as well. So it's the recursive aspect of these zero-knowledge proofs, or recursive snarks, that allows us to decrease the size of the blockchain immensely. Because now we're not storing the actual transaction data, we're merely storing the proofs that the transactions have happened. And that's more important than the transaction data itself. All right, does that make sense for everyone? Does anyone have any questions so far? All right, well, if you do, some quick drawbacks are that it takes a lot of time to produce these zero-knowledge proofs. It can take up to hours. And on top of that, there's a trusted setup in the beginning that is required for certain types of zero-knowledge proofs. Zcash, if you've heard of it, had this key generation ceremony in the beginning where everyone went into the desert, well, not everyone, but some people went to the desert or wherever, into an isolated area, generated some random number, and then shared that random number between themselves in some ceremony, and that is the source of randomness for Zcash. The issue is that if all of these people had colluded, they could forge any transaction that they wanted to, and they could trick the network into thinking it was valid. So again, you see trust in the context of blockchain, you probably cringe, and that's appropriate. So there are some things known as bulletproofs which don't require trusted setups, but that's a matter for the anonymity lecture. Yeah. All right, so these are all the naive things we can do, right? This is just the naive steps that we can do with the blockchain. So what other things can we do beyond just changing the blockchain? All right, so if you do have any questions and you try to speak up, you're free to ask in the discussion section for the next 5 minutes. All right, go ahead.
Oh, sure.
Segway, from a high level, it just means that
I'll walk it around. Yeah. Moderate everything.
Say whatever.
Did you by chance start a timer? Okay. No, you're fine. All right, we're in section 3 and I'm at 7. Is that too fast or too slow? Okay.
Yes, the morality is like no it's more or less. You're already doing like
It is also privacy, but in this context, we're talking about scalability benefits.
It's not really like it's not really as it's still like
All right. Okay, it's 7 o'clock. Let's go ahead and get started with the second half. Section 3. All right, does anyone have any questions so far that they haven't yet had answered in discussion or otherwise? Okay. Just giving you a chance before we get even deeper into this topic. Okay, cool. All right, so now that we've explored like the options of how we can change the on-chain parameters, let's look at how we can attach different technologies that are not on-chain but are still able to help us scale the transactions per second. All right, so there's a lot of operations that we do on the blockchain which you don't necessarily need to do. All right, so one issue is that we have these very long wait times for blocks. We wait 6 confirmations. All right, that's an hour on Bitcoin because we want to make sure that our transaction's been finalized. We also have high fees on the chain. All right, these are obviously bad. I mean, kind of, no one says I want more fees, you know. All right, so what is a way that we can reduce the burden of the blockchain while still keeping our transactions secure? So think about how a centralized system works. Right? When you have peer-to-peer transactions, you don't go and tell everyone else about it. You just interact with the person who you're talking to. So if I'm sending Bitcoin to Gloria, right, is there a way for me to send Bitcoin to Gloria and for Gloria to send it back to me without us having to inform the entire room that we're making the transaction? This is the concept of a payment channel. Right? So in payment channels, you maintain a private balance sheet between yourself and some other person. And this balance sheet is a record of all of the transactions you've made since the inception of the balance sheet. Right, so this is very straightforward. You update it whenever you make a transaction, and you only consult the blockchain when you are generating or closing the private balance sheet. In other words, the blockchain acts as the source of truth at the end and in the beginning when you're constructing the balance sheet. So the way it would look is that there's some funding transaction somewhere in the blockchain. Alice and Bob will privately exchange Bitcoin, and then once they're done, whether it be after some time period or whenever they choose, they then close the balance sheet. Great. Hopefully this is pretty straightforward. Are there any questions so far? Mm-hmm.
With that pictures of blockchain like running up.
Oh yeah. This so the pointers are to the previous blockchain or the previous block hash. So yeah. Yeah, so it's growing down that way. Yeah, my bad. This is a little confusing. All right, cool. So how can we actually do this in Bitcoin? Well, we can use Bitcoin scripts, which we have access to. Now, Bitcoin scripts are not the most powerful mechanisms for producing any kind of like functionality, but what we can do is create what are known as hash time-locked contracts. And it's called a hash time-locked contract because it can be unlocked by one of 2 things, a hash or a certain amount of time passage. And the contract because you're setting up an agreement with someone that you're going to lock up Bitcoin into a certain transaction until certain conditions have been satisfied. Right, so it's sort of like a smart contract except in the scope of Bitcoin. So this is a confusing diagram. I thought about copying and pasting the one from the white paper, but I don't think it would help anymore. So please follow along with my words, and if you have any questions, please ask. All right, so this diagram right here demonstrates the various information that's exchanged in the Lightning or in the payment channel whenever 2 entities are interacting. So let's say you have Alice and Bob. Alice starting with 10 Bitcoin and Bob starting with 0. Every time they make a transaction, like this first initial transaction or this first initial state, there should be, at any given point, the ability to close this payment channel and get their Bitcoin back on the original chain. So if Bob were to if Bob wanted to claim his Bitcoin, so Bob can publish one of 2 columns. Or Bob can publish one column and Alice can publish the other. So if Bob wants to close the payment channel, he can publish that column on the right. So he will publish the transaction with Alice's signature being able to unlock it. And he'll also publish this funky little guy right here. All right, actually, let me back up. I think I got a little bit ahead of myself. So the issue with this payment channel is that when we're making transactions in privates, no one knows what the most recent state of our private balance sheet has been. If any person in this payment channel, if either person wanted to go back to a state where they were like in a better position. Like say I was exchanging Bitcoin with Gloria. I started off with 20, she started with 10. And then at some point she has all 30. I would want to publish the state at which I had 20 and she had 10 in order to get my Bitcoin back. Right? That sounds like something that anyone would want to do because it's in their favor. This means that we have to have a way to ensure that any state that is not the most recent state is invalidated. And that is what these secrets here inside of the blocks do. I mean, these aren't blocks in the sense of like Bitcoin blocks, but rather these are categories of transactions. So every time that Alice and Bob generates a transaction, they will also create a secret for each transaction. When they create a new transaction, right, when the state is updated, they're then going to share their secrets. If you can see over there, this value over here has been revealed, and that value up there has been revealed. Every time that a transaction is made, they will exchange the secrets for the previous state. Now let's say that Bob, let's say that he were malicious, right? Or no, let's say that Alice were malicious. All right, so in this case, Alice is 10. All right, when it gets to this step, Alice wants to get her Bitcoin back. So she, instead of publishing this version of their payment channel, she tries to go back in time and she publishes this one. Alice is allowed to publish this column right here. She can publish a column in which Bob can get his Bitcoin back with his signature, but in order for this Bitcoin that was owned by Alice to be unlocked, you need one of two sets of inputs. Either you need Alice's signature plus 1,000 blocks having passed, or if Bob were to see that transaction, he can give his signature and the secrets for that transaction, and he can take the Bitcoin. Now keep in mind that that transaction will not be published unless Alice chooses to do so. All right, so in that scenario where Alice was trying to cheat and she was trying to take back her Bitcoin, Bob now has the secrets to steal her Bitcoin. So assuming that Bob were to notice within 1,000 blocks, if Alice tried to publish that specific column that was invalidated because they made more transactions, he could steal all the Bitcoin in the payment channel. Well, not steal, but like as a penalty, he would get it back. All right, so only this column could be published such that Bob could get his Bitcoin back right away, but Alice would have to wait 1,000 blocks. Bob could not steal it because he doesn't have Alice's secret for this one. But if they made a second, if they hit stage 2, then in that case, publishing either of these would, or the secrets for these would be exchanged, and publishing either of them would mean the other person would be able to take all the money. All right, the point behind all of this actually is not as important as recognizing that payment channel's focus is in order for two people to be able to exchange information privately, but this shows that no one can be cheated even though the payments are private. Right? So the happy path is that people will publish the most recent states, but in the scenario where someone tries to cheat and publish an intermediary state, they can be punished because the Bitcoin will be taken away if the person notices within the time that's allotted. Cool. So are there any questions actually so far?
Oh, I didn't understand that.
Okay. All right, we'll go more into it in discussion, so don't worry.
Is 1,000 blocks arbitrary?
The 1,000 blocks is mostly arbitrary. Yeah, it just needs to be some longish period of time. Yeah, because if it's 10 minutes, right? If Alice knows Bob's asleep and Bob's machine is not doing his work for him, she could publish it, take the Bitcoin in the next 10 minutes. So 1,000 blocks is just some large period of time where Bob would probably notice, but not so large that Alice would be discouraged from opening a payment channel in the first place. Yeah. All right. So what are the goals here? So if either Alice or Bob cheat, because they give essentially the private key for any previous intermediary transactions, if any of them cheat, they've given the other person the ability to punish them. Right? So cheating is going to end up to more losses than it will any gains. All right. And on top of that, if Alice and Bob are cooperating, they never have to look to the blockchain. They never have to wait for the 6 confirmations or spend a large amount of money on fees, because all they're doing is exchanging money between themselves. And on top of that,
Game theoretically, would you want to wait till 999 blocks have passed, and then if you're trying to cheat,
right?
You have to be paying attention in the last 10 minutes. If you don't pay attention in the last 10 minutes, you can get robbed, basically.
So the thing about that is that the 1,000 blocks comes into play when the closing transaction is published. So it's from the time that the payment channel is closed, 1,000 blocks onwards. Yeah.
Where's everything deposited?
That's a good question. Everything is deposited between Alice and Bob's local computers or local wallets. So only those two are able to see the information as well. So this is also a privacy advantage, but we see it more as a scalability solution. Yeah. So if Alice's machine was to die, she would lose all her information if it weren't backed up. That's a good point too. Yeah. And then only two transactions are on the blockchain, the funding or opening transaction and then the closing one that ends up resolving the payment channel. All right, so there are a couple of issues which you may have noticed. One is that in order to open a payment channel in the first place, you need to lock up capital. You can't spend Bitcoin in two places at once, or at least you shouldn't be able to. So anytime you want to fund a payment channel, you have to lock up that Bitcoin in the transaction. All right, so that's not necessarily a bad thing because you can still use it somewhere else, but it's still a consideration. All right. And an issue is that with a payment channel, Alice and Bob are only capable of sending between themselves. If I want to send money to someone else like Alan, am I going to have to open another payment channel? How is that going to work? So this is where the ingenuity of the Lightning Network comes in. It's not just an ability to make payment channels, but an ability to make a payment channel network. It's a network that allows me to leverage any of my peers' connections and for them to do so as well, and so on and so forth, until essentially you can reach anyone in the network, assuming you have enough connections. So if Alice wants to send money to Charlie and she does not have a direct link, she can leverage her existing links and they will pass on the payment for her. And there's some fancy cryptography to make sure that doesn't get confiscated. But for the sake of time, we've left that out of the lecture. I mean, it's not incredibly fancy, but it's still not completely easy. Well, the point is that we can securely have Alice send money through intermediaries to Charlie without any risk of her money getting stolen. All right. And of course, if you're interested in more, if that wasn't meaty enough for you. All right, so how does this help scalability? Well, first and foremost, if we assume that there's enough capital locked into these payment channels, you really never have to reference the blockchain in the first place. You can make instantaneous payments, and you don't need to wait for confirmations or have to pay any fees. Right? So the only delay, the only latency is instead of having to wait for consensus, it's however much bandwidth your machines have between each other. Yeah, and only to use the blockchain when you're settling disputes or whatever else happens. So the blockchain just serves as like a essential source of truth that really does not matter when you're doing these payments. It's just because of the fact that if there's an issue, you need something to reference, and that's when you end up involving the blockchain. Yeah. So now we have transactions per second at a rate comparable to Visa, if not more. Haha. Yeah, so actually this is already implemented, so if you want, you can already start using the Lightning Network. It's been implemented for a while now. Yeah, but it's just cool to see that when this was first made, this was still just a white paper. This lecture being, when this lecture was made 2 years ago, the Lightning Network was still just a white paper. Yeah, and that's those are all the benefits of the Lightning Network. Some of the cons are that now these nodes need to keep large amounts of capital locked up within these payment networks. And on top of that, there is a strong centralization force, which means that nodes may want to centralize. Nodes with a lot of capital will be able to support a large amount of connections. They might leverage fees on you using their connections. Like, let's say Bank of America starts using the Lightning Network and has a lot of Bitcoin funded in a bunch of payment channels with a lot of other people, a lot of other popular suppliers like Walmart and Uber. Then it would be easy for you to just go through this one path, but they might also leverage fees, which then creates another source of centralization and fees, which is undesirable. Yeah. So this type of topology obviously looks more like a centralized solution than a decentralized one. All right. And Raiden is not that much different from the Lightning Network. It's just the version of it on Ethereum. Yep. It's pretty much as simple as that. All right, so go ahead and take 5 minutes for discussion, and then if you have any questions, if you didn't understand anything, please feel free to let me know. Cool.
Sure. Okay, so what's the well, like the idea behind it. Okay, so you have a statement that says each so you have to come so when you want to so you don't want to reveal the right states. The fear is you reveal old states. So there's like a counter in the states. So when you give me this picture like I say, oh, it's not the correct state. So I'll put the newer one on, and it's going to have a later time step, which is going to validate that.
Something like two people want to send each other money. Instead of the very last state, like instead of like having those transactions on blockchain, they create channels so that like however much money they want, and all the transactions there, and then the final transactions like it's just like
Yeah, I would have to
Just the idea about having the sequence and then using those to validate so the main psychology with the is that if you have there's no way to
you're saying that I publish it, and then you pay me, and now you change the scheme.
so for instance, if you post an A versus B in a channel, A has 10 bitcoins,
No,
and then A sends B all of his bitcoin.
no, the latest
So that
statement
B has
that's
10
there at the time of termination corresponds like
A can end up saying, oh, I'm
so
going to publish this
like
A
in the
where
scenario
I
like okay, I
and go back
I start using window some
So the
state
idea behind all this is we need a way to
and that's and you can put that on chain. Then and we're in the scenario where I get more money, you get less.
So how do we
why
do
would you want
this? The way to do that is when A sends
yeah.
so he not only sends his signatures, but also a source. And what that secret statement is proving that the past state was invalid.
So you have any questions, sir?
So in state 1, when A sends B to C, that proves that state 1, when A sends B, is invalid. So now if A tries to publish C, he can say, hey, you've already
Oh, except
that's perfect.
Like how much you are
there's no long run.
So you have to you want all of the
I was getting confused with lightning. They have this thing that is they have this thing where and they're you can go multi-class. So trying to form like a network of all these connections. Since we did routing protocol, and the routing protocol needs you to know like who everyone else is. So sometimes you have things like most of the so like the one example is that other
so like because you lock it because at the end you're only manipulating like if I have 10 bitcoins, we're only manipulating 20 bitcoins regardless of how many transactions.
so
You do like 50 transactions, it's still 20 bitcoins. So if you when you
a side chain is the idea like there's a main chain and then this other chain and like these two like somehow the side chain has manifestations of the main chain to like finalize the state or checkpoint the state. So sorry, let me backtrack. The side chain will
if they don't lock it, they only can use that data again. So
and
if you have 10 and I have multiple, it can be 5 or even 10. I can still 10.
that's all mine. But I can't start with anything. Like I can't do anything. And like when that system is wrong, doesn't mean that Bitcoin is right still.
But you prefer the Lightning networks, and then like how centralized, like how it can possibly it can be centralized because we like
Oh yeah. So
someone who's large enough to be able to like it's other people some seconds you have an outlet for this channel or something like that. Doesn't that just like take it to like the way it is now in terms of like decentralized banking
Yeah.
Yeah, so that's
Yeah, you have like Lightning service providers who have all these connections, and you leverage them for a fee.
yeah. So what is the point of the system that's not the exact same as
Right.
today's systems?
Well, that's a philosophy question, right? Because it's still decentralized. No one controls your private keys. No one controls your account. Right? If you have an issue, you can go back to the blockchain, which is decentralized.
It's more or less you're sort of if you don't want all your freedom, you can adjust it so you can get something that's you lose some of that freedom in exchange for more flexibility.
It's all on the spectrum. Yeah. All right, cool. It's been 5 minutes, so let's go ahead and get onto the fourth section. All right. So does anyone have any questions before we go into this? Cool. Horizontal scaling. All right, so we've talked about vertical scaling on-chain and off-chain. Now we're going to talk about horizontal scaling, which is taking the same amount of machines but allowing more work to be done. All right. So traditionally, sharding, which you may have heard of before, was referring to just typical databases. Rather than having each node in the database, in this distributed database, store all of the information about every single user, you split them up by region or by whatever made sense. And that way, each database only needs to hold a certain subset of the total information. And if you wanted to recover all the information, you'd have to go to all of the different sub-networks or individual nodes and ask them what it is that they know. All right? And the way that this corresponds in, for example, blockchain, is you could split up transactions or users by something arbitrary like the range in which their account falls. Like if you have all the users less than 500 in one database and all the ones above it in another database, what this allows you to do is have different sub-networks which work in parallel to process transactions. So traditionally you can see Ethereum as one big subnet or one big network, right, where everyone does the same computation. If you split it in half, you now have two networks which are both doing their own transactions, and at the end they will come together and reconcile whatever transactions they produce in their sub-networks, and then that way you're processing twice as many transactions at once. All right, so sharding is the idea that not every single node needs to be working on every single transaction. All right, and this is a very straightforward concept when it comes to like understanding it conceptually. Of course, implementing it is a completely different question, but the idea is that you've now split the network into certain portions, and each of these portions has its own method of making sure that nothing goes wrong and validating transactions, and then there's some overhead which allows you to merge all these transactions together. And then because of the fact that you've now defined a way in which certain nodes have some information and certain nodes don't, you're also able to classify the types of nodes that you have. In other words, you've created some stratification within this database. Okay, so certain nodes might be super full nodes or just top-level nodes, meaning that either they store all the information or maybe they store all the block headers, or maybe they're just part of a small subset, or maybe they only have like a tiny bit of information. All right, this allows for a great number of options when it comes to what kinds of nodes you can run, and it also decreases the amount of work that any individual node, or it increases the amount of work that the whole network is doing, because not every node has to run all the computation. Right. So there are some big challenges which are pretty obvious, like cross-shard communication. Right, if I have one network, how do I ensure that my findings are going to be able to merge with the findings of another network? How do we ensure that if one subnetwork is not trustable, that we either detect it and reject it, or ensure it never happens in the first place? Right, so what are the ways in which we can prevent malicious behavior from happening? That's the important question, and that's one that's very hard to answer in the blockchain scope. right? Sharding is very easy to, or it's easier to implement rather in centralized systems because you have control over everything. In decentralized ones, where you don't have control over everything, there's no set number of nodes, there's no set number of users, right? Everything is difficult to predict and manage, and for that reason, there's a lot of challenges and a lot of different outcomes that might happen when trying to implement sharding. Right. Are there any questions so far? Right. So sharding is one example of horizontal scaling, in which you're taking the same number of machines and you're making more work possible. Another possibility is what's known as a sidechain. And a sidechain is the idea that if you cannot speed up a protocol, why not create a separate chain that interacts with this protocol every now and then, and that way you can do whatever expensive work you need to do there and then come back to the Bitcoin blockchain. It sounds familiar, it sounds like the Lightning Network. The difference is that instead of having private payment channels, you have an entirely different blockchain. And that blockchain can then communicate to the original chain through what are known as pegs, or two-way pegs specifically. So if that is the Bitcoin blockchain, the one in the center, these circles are just for, I guess, graphic design. They're not technically correct, so just intuition, I'll just say that. So if that one in the center is the Bitcoin blockchain, then it can connect to other blockchains and those are other side chains. And those side chains can have even further side chains. And each of these side chains can have an individual purpose. And by having each of these side chains have an individual purpose, you now give each of them the opportunity to do whatever expensive work they want to do over there in their own circumstances while not putting that burden on the Bitcoin blockchain. And you reference the Bitcoin blockchain when you want to resolve anything. Like if you're finished with work on a side chain, you go back to the Bitcoin blockchain. And that's the base layer of trust. And then any side chains are whatever specialized stuff you want to do. So as you can see,
Do users within a sidechain, can they only send to people within the sidechain?
All right, so the question is, do users within the sidechain only interact with users in the sidechain? The answer is yes. A sidechain is like a sub-network in which users are doing whatever particular work they want to do. They would interact with the main blockchain whenever they're taking their coins from one blockchain into another. Yeah. So there's no interaction beyond specifically that when you're moving coins from one to another. Yeah. All right, so are there any questions about any of these two between sharding and sidechains? The idea is just that you take the machines and you split them off into their own network, and that separate network is able to do work in parallel to whatever you're doing. And by that, you're able to have more transactions per second with the same amount of machines. How many people have heard of rootstock before? All right, rootstock is it's a way to bring smart contract functionality to Bitcoin. And the way it does this is actually through a sidechain itself. Rootstock, you can do whatever smart contract logic you want on it, similar to Ethereum. I mean, not quite, but conceptually, you can have any smart contract you want on rootstock. And when you want to turn those tokens back into Bitcoin, you use a two-way peg. So essentially, you've brought the functionality to Bitcoin even though you haven't changed the protocol at all. It's a separate protocol, separate network. And while you can see that it means that you now have to have a separate amount of miners, you have to have a separate team that's developing this protocol, everything's separate, but at least you can connect it to the original Bitcoin blockchain and leverage that thing, which is already trusted by the rest of the network. Cool. If there are no further questions, I will just go ahead and dive into the advanced scaling and generalizations. So we've talked about vertical scaling. We've talked about horizontal scaling. Now we're going to take it a step further and talk about diagonal scaling, which is doing both of those things at once. And this is where Plasma comes in. So the thing about Plasma is that it allows you to create a sub-network in which you have some transaction you make on the Ethereum chain, and that produces a child chain. And in that child chain, you can produce further child chains. And in that way, you have diagonal scaling, because not only are you able to create sub-networks, but also each of those sub-networks can make further sub-networks. It's like a recursive structure. So now each of them can do more work, and you've taken more burden off of any of the parent chains. And of course, any time that you want to resolve any issues, you go back to the parent chain to resolve it. Right, so you deposit some Ether into the root chain smart contract, and then that deposit will show up on the other side. And any time that you attempt to exit, then it's all resolved by the main chain in the end. And actually, there's a Blockchain Berkeley team working on this known as Fourth State Labs, and they're one of the most popular implementations out there, actually. Yeah, so they're using the Cosmos SDK in order to implement Plasma, because Cosmos, as we'll talk about very briefly, is a way to connect different blockchains. And of course, connecting blockchains sounds a lot like what Plasma is trying to do. So if you're interested, of course, feel free to look them up. All right, so Plasma is just one component, really, of this larger ecosystem. And actually, the thing about Plasma is that it builds off of this other project known as Cosmos, and you'll see how these interact. So this stack right here is the stack which Cosmos defines as sort of like the blockchain stack. You have the networking layer, you have the consensus layer, and the application layer. The networking layer is the mere ability for peers to talk to each other. The consensus layer is the ability for them to agree on some state of truth, update the blockchain. Then finally, the application layer is the ability for someone to write some logic that can then be powered by these bottom two layers. All right, so what Cosmos tries to do is it tries to produce a protocol in which you can write applications that can connect to any other blockchain. Hence their motto is the Internet of Blockchains. And they produced a consensus algorithm, which we've talked about before, known as Tendermint, which provides those networking and consensus layers. And you can build arbitrary applications on top, which are connected through the application blockchain interface. And Cosmos uses that in order to build what are known as these Cosmos hubs and zones. So the hub is the source of truth in this case, and the zones are individual blockchains. So vertical scaling, the speed of the consensus algorithm Tendermint, is what provides vertical scaling, and horizontal scaling is brought by the interoperability of all these different subnetworks together. So each zone can process transactions individually, and whenever they want to exchange information between each other, they'll go through the hub in order to send that information. All right, so this is a more complex way to show what I just described, if you like that. All right, cool. So obviously you can see that there are a great number of ways to go about making consensus algorithms. I won't get too much into this, but the point is that if you're building out a system, there's a great number of different possibilities. Right, so anything we're talking about in this lecture, these are the specifics. It's just for you to get an idea, intuition behind what there is that's possible and how it's made possible. All right, let me see. All right, so I'm actually going to, so there's a lot of different questions here that I guess are better suited as discussion questions. But the main question is, one, scaling is not just a technological problem. It's also a philosophical problem. What is it that you value when deciding what to scale, what burdens to take, where to put those burdens, right? And also, what is your end goal? Is your end goal pure decentralization? Is it security? Is it scalability? Because all of those things, as we mentioned with the trilemma, are going to end up challenging one another. And of course, there's all these different questions about what you're scaling, where you're scaling, and any of the concerns that could arise from those different types of approaches. I was asked, what's a way in which I could write some code that demonstrates what I've learned from the scalability lecture? And the answer is you can't really. It's much more of a design level consideration than it is I'm implementing a scalability solution. You could implement something like Cosmos or implement something like Plasma, but in order to understand what it is that you're doing with those, you have to understand the general scalability concerns and what you're doing to modify the current form of the blockchain protocol. And back to this trilemma. Right, so anytime that you're trying to achieve one of these three, you often end up compromising two of the other ones. All right, and then it's a long list of summaries. So we first talked about the vertical layer 1 scaling, where we naively modified some of these block times, sizes, and we demonstrated the Ghost protocol, Segways, recursive snarks. We talked about going off of the blockchain and payment channels, the Lightning and Radiant network. We moved to horizontal layer 1 sharding. We talked about sidechains, Plasma again, and Cosmos. And then finally, alternative structures or consensus for scalability. Yeah. And that's basically it for the lecture. If you have any questions, feel free to ask. Otherwise, we'll spend another 5 minutes or so of discussion, and then we'll have the quiz. All right, cool.